Everyone, I'm going to present this paper called CTracker, which is short for Chain Tracker, and it was published in ECCV 2020. The content of this presentation follows the same structure as my previous presentations. It has abstract introduction. It reviews the contribution of the paper first, and then it dives deep into problem setting, frameworks, implementation, network architecture, and so on and so forth. And at the end, I have trained the models of this paper, and I present my own results at the end. And we conclude this presentation by giving a conclusion part. Right. As for the abstract, multi-object tracking has three subtasks. Usually it has object detection, feature extraction, and data association. And previous works usually did these steps separately, and the chain tracker model integrates all these three into an end-to-end solution. This model chains paired bounding boxes regression results estimated from overlapping nodes, and each node covers two adjacent frames. The pair regression is made attentive by object attention, and the two major novelties in this works are chained structure and paired attentive regression. I know that a lot of these texts might not seem interesting or sound to you right now, but at the end of the presentation, they make a lot of sense. All right, so I have this visualization over here in which it explains that previous frameworks used to perform object detection, feature extraction, and data association separately, or they would have joined a number of them together. But CTracker, to the claims, to the best of knowledge of the authors, are the first model that is combining all these three together. MOT still remains challenging to the following facts. The first one is occlusion, the second one is trajectory overlap, and the third one is crowded background. And there are some major problems with tracking by detection, which is the basic and conventional method of tracking these days. It presents suboptimal solutions. And the reason is obvious because detection, feature extraction, and tracking are done separately. Tracking depends on the performance of detection heavily, and one cannot optimize it thoroughly. And it takes complex method to improve. For example, attention and ID verification have proven to be valuable assets, but adding them increases complexity and computation time. There are two tricks that can boost MOT performance. First of which is re-identification, which extracts better features, and the second one is attention, which makes the model more focused on important details. And the new model that the author presents solves the previous problems. It takes adjacent frame pairs as input. It performs joint detection and tracking in a single regression model. It regresses the paired bounding boxes instead of one bounding box. And it uses the attention to improve its performance. There are two kinds of attention in this network. The first of which comes from the classification branch, and it helps the network to focus on the foreground regions. And the second one comes from the re-identification or verification branch, and it helps the network to focus on regions corresponding to the same object. The contributions of this fork, in short, are as follows. They solve the three subtasks at the same time. They use a joint attention module to highlight informative regions, and they achieve the state-of-the-art results on MOT 17 and 16. As for the problem setting, the MOT problem is represented below. So given an image sequence, MOT predicts all the bounding boxes of their corresponding identity labels. So f of t here are the image sequence, as G is ground truth and Y is the detections. As the framework that CTracker follows, most MOT models, as we discussed, only take a single frame as input, but CTracker requires two adjacent frames as input, and it is called a chain node. And the first chain node is F1 and F2, which are frame 1 and frame 2 as a pair. And the last chain node is Fn and Fn plus 1, in which Fn plus 1 is just a copy of the last frame. And given an arbitrary chain node of Ft minus 1 and Ft, the model generates bounding boxes pairs, which are denoted as dt minus 1 and d hat of t. Similarly, for the next node, Ft and Ft plus 1, the model generates bounding boxes pairs dt and d hat of t plus 1. Please note this hat over the next, over the second part of the pair, which is important. So two adjacent nodes have a common frame, and the detection in that common frames are denoted as d hat of t and dt, which are the detected boxes in a common node. And the assumption of the author, this is the key assumption of this study, is that these two detections have to have a slight differences between them, right? And that brings in the node chaining idea. Assuming that d hat of t and dt are slightly different, one can use a simple matching algorithm to match them. Node chaining has the following steps. So every detected bounding box is in D1, initializes a tracklet with new ID. For an arbitrary two nodes, they calculate the intersection over union of the detections of the frame that they both have, and based on that intersection over union, they use KM algorithm to match boxes. And if there is no match in the new node, they will initialize a new tracklet, and if there is a match, they will update the previous tracks. The chaining is done sequentially over all adjacent nodes, and it builds long trajectories for individual targets. The things that I discussed are visualized in this picture, in which CTracker has two adjacent nodes, and these two adjacent nodes have Ft in common. And they are using intersection over union for the common frame to match bounding boxes, and these matching can extend the trajectories. And to make this model robust, they are choosing to keep some of the terminated tracklets up to sigma nodes, and sigma is a hyperparameter which is set to 10 for this work. Yeah. And there are also limitations in this for this model. This model is effective for handling temporary occlusion for sigma frames. It has detection latency, meaning that if an object is not in frame t minus 1, but it appears in frame t, it will be detected in node Ft and Ft plus 1. Instead of node Ft minus 1 and Ft, and the same thing holds for disappearing in frame t. The chaining process is not differentiable, and therefore the method is not fully end-to-end, but the author are calling it end-to-end anyways. As for the network architecture of the CTracker, it follows a straightforward detection architecture with the following key points. It has a ResNet 50 backbone, which extracts high-level semantic feature. It has a feature pyramid network, which extracts multi-scale feature representation, and feature maps of adjacent frames are concatenated and fed to the prediction network. Prediction network in this of the CTracker has 3 branches. It has a pair boxes regression, it has object classification, and it has ID verification. And between them, there exists this joint attention model, or JAM for short, with 2 complementary attentions, one of which comes from the classification branch, and the other one comes from the re-identification branch. Yep. So this is the architecture. As I told you, the 2 frames are fed into the same network, which are sharing weights, and the results are combined and concatenated into one space. And there exists this 3-branched network, in which each branch is performing a separate task, and there exists object attention between separate branches, and at the end, a paired boxes regression is performed. This network, to train this network, one has to create labels and loss functions for classification, for object classification and object re-identification branch. And for a arbitrary node denoted with ft and ft plus 1, let's assume that we have an anchor which is pretty common in detection, and it is denoted with a capital A of t. So the thing that they do is they use ground truth bounding block matching, and they store those matching into a matrix M. If the intersection over union of an anchor and the ground truth is greater than a threshold, the element in the matrix is 1. If it is less than a threshold, the element is 0. And based on that matrix M, one can assign a ground truth label for classification, which uses the matrix itself. And the same thing holds for re-identification. Here, I is the identity of the two ground truth, and C is the previous label that we discussed. So it says that if the identity are the same and the object detection label is also 1, the ID verification label is also 1, which makes sense. And for the regression ports inspired by faster RCNN, they are trying to regress the difference between anchors and detections and ground truths. So we have a delta D and a delta G. Delta D represents the difference between the anchor and the detection, and delta G is the difference between the anchor and ground truths. And the model is trying to regress delta G based on delta D. With that in mind, the regression loss is the difference between delta D and delta G in frame T and also in frame T plus 1 with L1 smoothness divided over 8. And the overall loss is the regression loss plus a loss for classification and another loss for re-identification. The data set that they use in this study are MOT16 and MOT17, and to evaluate the models, there exist these very standard measures named clear MOT metrics, which consist of MOT accuracy, MOT precision, false negative ID, false positive ID, ID switches, percentage of mostly tracked trajectories, mostly lost trajectories, and IDF1 score. Here we have a sample of MOT17 dataset in which you see that people are walking around and there exists bounding boxes around them. As for the implementation details, we are using PyTorch 0.4, which is an older version, but this is the one that was compatible with SoftNMS library. The optimizer is Atom. Learning rate is 5 times 10 to the power of -5, and the model was trained up to 100 epochs, and the batch size is 8, which is 4 pairs. Initialization method is K-Ming. Data augmentations that were used are random crop and random flip. Loss hyperparameters alpha and beta are set to 1. Anchor matching thresholds TP and TN are set to 0.5 and 0.4. Soft NMS threshold is set to 0.7, and intersection over union matching threshold is set to 0.5, and retention threshold sigma is set to be 10. The authors did an ablation study in which they tried to figure out if all the part of the networks are necessary. So they have this baseline of only one regression branch and classification branch, but there is no attention. The second step is adding attention between object classification and regression branch. And the next step is to add ID verification with no attention. At the last step is the CTracker. And they show that adding each component improves the overall performance of multi-object tracking. They also evaluate their models on the benchmarks of MOT17 as MOT16, and as shown here, they achieve state-of-the-art results on both MOT 17 and MOT 16. And there exists this qualitative results for the CTracker also, in which you can see that the bounding boxes are actually pretty accurate. As for my study, I wasn't able to train the model for 100 epochs because it took a lot of time from me. I trained my model for 10 days on NVIDIA GTX 1080 for 55 epochs. And I evaluated my model on the train set, and the author also presented the table 1 for their model. So as shown here, for most cases, my model is not as good as they, but it is pretty close. And I believe that if I had enough hardware resources, I would have achieved the same result. But again, it is only MOTA in which my model is performing good, but looking at false negative or ID switches, it is obvious that my model has a lot of room for improvement. And after all, this study was published in a reputable journal, so they must have done a pretty good job of training the network. And in conclusion, a novel joint multiple object detection and tracking framework was presented. Different from existing methods, they use 2 adjacent frames as input. The network regresses a pair bounding boxes instead of 1 bounding box. Guided regression by a joint attention module, and using the simple intersection over union overlapping nodes can be changed. And experiments on MOT benchmark demonstrate the superiority of this work.